Hello, my dear students. This is Sensei. In this video lecture, we are going to talk about the work energy theorem. First, I will be giving you two scenarios, and I'd like you to identify which object is doing work on another. In the first scenario, you watch your bowling ball rolling down the aisle and felt that you did a good serve. And true enough, the ball hit a strike and all of the pins toppled down. Outside, you saw a crane operator swinging the wrecking ball like a pendulum to demolish an old building. When the wrecking ball hit the structure, pieces of the walls broke apart and projectile to the ground. In the first scenario, it is the bowling ball doing work on the pins when it displaced them. Meanwhile, in the second one, work was done by the wrecking ball on the old building's walls. The motion of the bowling ball and the wrecking ball allowed the two to do positive work on another object. So, an important observation is this: moving objects can do work. However, another less obvious observation can be had. That is, when work is done on an object, the receiver of the work experiences a change in speed. In the previous examples, both the bowling pins and the old building's walls were at rest at first, but after work is done on them, they began to move. This also happens when you are driving a car. When the accelerator is pressed down, the car speeds up, but when it is the brake pedal that is pressed down, it slows down. This brings us to the work energy theorem, which relates work and kinetic energy, or energy of moving objects. It states that work changes the speed of the object and ultimately its kinetic energy. In equation form, the work energy theorem is stated this way: work is equal to the change in kinetic energy of an object, or the final kinetic energy minus the initial kinetic energy. Just take note that the work we are referring here is the net or the total work on the object. So for example, if a box is pushed and it costs 10 joules of positive work, but frictional force is doing 2 joules of negative work at the same time, the work to be considered is 8 joules, or the net of the two works. The work energy theorem is very useful in solving braking distance problems. If, for example, you have a car of known mass and you wanted it to slow down from a higher speed to a much lower speed, you will know exactly how much work is needed to do this. In breaking down a speeding car, the force doing the work is the force of friction present between the tires and the road. This is evident in the skid mark left on the road when braking at high speed. But did you know that whether the car is moving at high speed or low speed, the maximum friction the brake can apply is nearly the same? In other words, if you want to stop two cars, one moving, let's say, at 20 meter per second and another at 30 meter per second, you can apply the same maximum friction. The only difference is between the two, the slower car will take shorter time to stop. Their braking distance, or the skid mark, the faster car will leave on the ground is, or will be, longer. Remember, the kinetic energy depends on speed squared. Let's take a look at this simulation to further elaborate this. Below, we see a red car traveling on a highway at a speed of 20 meters per second. The driver saw a stop sign, took some time to react, then finally pressed the brake pedal. The car eventually stopped after traveling a braking distance of around 26 meters. Now, let us see how much longer the braking distance will be if the car is traveling at a faster rate of 30 meters per second. After reacting to the stop sign, the car started decelerating, but did not stop until reaching a braking distance of 58 meters. Take note that there are other factors to be considered when determining a car's braking or speed or stopping distance, such as the wetness of the road, the state of the car's tires, and the driver's reaction time. Driving an old car with thinning tires at fast speed during a rainy day is ill advised because there is little friction between the tires and the road, causing slippage. Also, distracted driving, such as using your phones while driving or driving under the influence of alcohol, is prohibited as they would slow down the reaction time of a driver. In summary, moving objects can do work on another object. When work is done on an object, it results to a change in its speed. It may either speed up or slow down. The change in speed also means that the kinetic energy of the object is also changed. In other words, work changes the kinetic energy of an object. In an ideal world, all work done is transformed to energy. But in the real world, frictional forces are present, which makes the transformation less than 100%. In braking distance problem, if the speed of the car is doubled, the work needed to stop it is quadrupled.